Okay, today we're going to go over the special problems with circular motion. Essentially, we talked about just general circles the first day, centripetal motion. Then we talked about vertical circles, and so we talked about, in general, top and bottom, how vertical circles work. Now we're going to have a couple special cases of problems, but they're all not too bad. First thing is a banked curve. So what this looks like is we have a car that's going against a curve, but it's basically going in a curve, but the curve is banked. So hopefully you've seen this before. If you need to, look up banked curve racing, and you'll see what it kind of looks like. It turns out that if you have a banked curve, there is a certain angle and a certain velocity you can have and a certain radius that everything lines up perfectly so that we don't need friction in order to turn. Okay? So normally whenever we turn on a flat surface, in order for us to turn, we turn our wheels and we create friction with the ground, and that causes our motion to turn. But with a banked curve, with the sloped surface, we can have the slope just right so that we cause our car to turn anyways without some sort of friction. And that's what we're going to talk about. And those are the equations we're going to deal with. And hopefully my iPad works. There we go. So what does that look like? Well, think about we have a car on a slope. Okay? And so we're going to start with a free body diagram. We're going to draw, we have two forces. We have gravitation down, and we also have the normal force at an angle. If you remember, when we did slopes before, we split up our components and we also tilted our axis. We're actually not going to do that this time. We only did that last time because our acceleration was down the ramp, right? Our box was sliding down the ramp, therefore we wanted to tilt our axis. But guess what? In this case, our car is not sliding. It's just moving in a circle. It's moving flat. And so we don't want to tilt our axis at all because our acceleration is actually towards the center. We're turning this way. If we were to look at the top of a bird's eye view of this, our car is like this. We're on this curve like this. And so our car is turning like this, so our acceleration is towards the center. So our A is towards the center. And so we don't want to tilt our axis. It's actually better to keep our axis as it is because that means our acceleration is in the x direction. So instead, we're just going to split up the normal force. And so if we redraw our forces, we have Fg down, but then we have a normal force in both directions if we split up the forces. And it turns out that we have a normal force in the cosine theta direction. We have a normal force in the sine theta direction. Again, and let me point out that our theta is the angle of the slope, just like normal. So it turns out f in sine theta is in the x direction, just like with slopes, and f in cosine theta is positive y, just like with slopes. If you remember that normally cosine is in the x, normally sine is in the y, but it's flipped when we deal with slopes, and it's also going to be flipped here. If you want more theory of how this works, make sure you email me and say, hey, Mr. Wilson, I really want to see the proof. Like, I want to see the trigonometry so I can really understand how banked curves work. If not, you just need to believe me that this is our free body diagram. And it's going to be the free body diagram for every single banked curve problem. Okay. Now that we got that, we can move on to f equals ma. We have two directions, and so we still want to do f equals ma in two directions. One for the x, one for the y. If you remember, we used to do t-charts. This is essentially a t-chart. I just didn't draw it in a t. If you want to, you can put a line down the middle. In the x direction, we only have one force, normal sine theta, and that's equal to the mass times our acceleration. But in this case, it's centripetal acceleration. We're moving in a circle, and so instead of writing a is going to be equal to v squared over r. So we're going to write v squared over r. Okay, great. What about the y? We're not moving up or down. We're only moving in the x direction. And so turns out our normal force, cosine theta, minus our gravitational force is equal to 0. just like with forces. And so it turns out that we can simplify this. That's actually not bad that I zoomed in. Except for that it messed with my work. Oh man. Okay. Sorry about all that. Let me erase all this. F in sine theta equals mv squared over r. All right, and so we can simplify this side. F in cosine theta equals mg. And I would box off this equation, and I would box off this equation. These are your two equations to solve your problems. The normal force times sine theta is equal to mass times v squared over r. So just your normal centripetal force equals mv squared over r, but now your centripetal force is equal to Fn sine theta, okay? And then on the right side, we just have the normal force cosine theta equals mg. Okay, this will solve most of your problems. If you're looking for V, if you're looking for R, if you're looking for normal force, this is going to solve all your problems. If you're looking for theta, I'm just going to go ahead and give you this. Again, if you want to see a proof for this, come to tutorials. I can show you the long proof for this. But to save time, I'm just going to give you the equation. Theta is equal to the inverse tangent of V squared over G times R. So you want to find your angle, you can just plug them into that equation real quick. Okay, let's see an example. So those are your three equations. A car travels on a banked curve of 15 degrees at 14 meters per second. What is the radius of the curve? Okay, so again, we have these two equations. T, my bad, not T. F in sine theta equals mv squared over r. And then we also have F in cosine theta equals mg. So we're given theta is 15 degrees. We're also given the velocity is 14 meters per second. And the mass is 300 kilograms. So it looks like to me we're looking for radius. We're looking for r. So that means we need to use this equation over here. We have to use that one for r. There's no r in any other equation. If you're looking for v or r, you have to use that equation. Unfortunately, I don't know the normal force. I know this because I know I can type in my calculator sine 15 degrees. I know m and I know v. I just don't know normal force. So if we want to find normal force, it looks like we're going to have to go over here. Solve for normal force here. So let's plug in this stuff. Fn cosine of 15 is equal to 300 times 9.8. Okay, we can solve that pretty easily. 300 times 9.8. Well, that gives me 2940. And then cosine of 15. I need to make sure I'm in the correct mode. I'm not. I'm in radians. Cosine of 15. It should be about 0.966. And so I'm just going to take this number and divide by that. So 2940 divided by that number. And I get my normal force is equal to 3043.71. And so now I can plug that all into the left side over here. So we get the normal force is 3043.7 times sine of 15 is equal to my mass 300, 14 squared over r, and we're solving this for r. So how do we do that? Let's simplify the left side first. Let's multiply that by sine 15. We get 787.77 equals 300. What's 14 squared? 196 over r. Great. Let's, what I want to do is anytime you see r on the bottom, we're going to go ahead and get it on top. I think that's the easiest way to do this. And so you're going to multiply both sides by r, so we get 787.77 times r is equal to 300 times 196. If you want to, let's simplify the right side first. So 300 times 196, we get 58800 is 787.77 times R. And then we can divide by this. Divided by 787.77. And you get R is equal to 74.6 meters. The algebra there at the end, from this point on, can be done so many different ways. And so if you did a different way and got to the same answer, awesome, you did your algebra right. And so don't worry too much about if you followed my algebra exactly. I try to do it in the way that makes most sense to most people, but I think there might even be easier ways to do the algebra, in which case do that if you know what you're doing. But if not, you can follow the way I did my algebra. Conical pendulums are actually going to be the exact same. If you look, so what a conical pendulum is we have some sort of, it's kind of like a normal pendulum, except for instead of just letting the pendulum drop like that, we push it into a circle. And so you can see the picture over here. We are pushing this thing around in a circle, and it still travels in a perfect horizontal circle, but it travels in a horizontal circle due to a rope at an angle. So imagine like a ball on a tether ball. You have the pole and then the ball's on the tether ball. You push the tether ball around and it circles the pole, and that ball stays at the same height constantly, but it just moves in a circle. It turns out it has the same free body diagram as a banked curve. Gravity is down and tension is at an angle. Look here. I'll draw it over here on the picture. We have gravity down and we have tension at an angle. Therefore, we're going to split up the components just like last time, where we have tension cosine theta and tension sine theta. Now, what is theta? If we draw the pendulum like such, your angle is this angle. It's the angle between the rope and where it should be normally. If you just let it drop and just settle, it would go straight down. And so the angle is between the rope and where it would rest to. And look, this is almost the exact same setup as last time, except for instead of normal force, we have T. And so the work is actually the exact same as last time as well. All the math and all the algebra is going to be the exact same. You're just going to have a different letter you're using. We're still going to have these equations. We're going to have T sine theta is equal to mv squared over r. And then we're also going to have the equation T cosine theta is equal to mg. And I would box off these two equations for conical pendulums. And then, of course, there's that third equation for the angle. If you're trying to find the angle itself, it's equal to inverse tangent of v squared over g times r. Same equation as last time. Pause here and copy them down. All right, so let's say we have a conical pendulum spinning in a circle of radius 2 at 5 meters per second. I want to find the angle it makes. Well, in this case, last time we practiced finding the normal force and doing all that, so I gave you this problem. I want you to use the angle equation. The angle equation is inverse tangent of v squared over g times r. Look, we have v and we have r. And guess what? We don't need the mass. It turns out it doesn't matter what your mass is. If you have a bowling ball or if you have a tennis ball, either way, if they're moving at 5 meters per second at a radius of 2, they're going to make the same angle because there's no mass in this equation, which means mass is irrelevant. That's besides the point. Let's just go ahead and plug in the numbers. Theta is equal to inverse tangent 5 squared over 9.8 times 2. So 25 divided by open parentheses 9.8 times 2. Make sure whenever you do this, you don't type in your calculator 5 squared divided by 9.8 times 2. you need the parentheses, because if you don't have the parentheses, your calculator thinks that you're multiplying by 2, and that the 2 is on top. So make sure you put parentheses in your calculator. You should be calculating theta of inverse tangent of 490. My bad. That's not correct. That's not correct at all. I didn't divide. 25 divided by 19.6. There we go. That's a more correct number. 1.276. And inverse tangent of that is equal to 51.9 degrees. So that's the angle we make. So that's actually a pretty wide angle. That's an angle of 51.9 degrees. Okay. Last problem is barrel of death. So this is just the way that we in physics call it. We call it the barrel of death. It's not probably a proper term. You might find it as other things on the internet. It's essentially, if you've been to the amusement park and you've been on the rides, like the Gravitron, you get in this big cylinder that spins really, really fast. So it spins like this. And everybody's standing against the wall, and everybody feels like they're going back into the wall, like them spinning forces them into the wall, like that. Okay, that's the barrel of death. But it also is the same as if you just had a cylinder and you had like a motorcycle guy. So like in this picture, this motorcycle guy's riding along the wall. And it's the same idea. We're just moving in a cylinder. And it turns out that on these rides, they used to, I don't know if they do it anymore, they used to drop the floor beneath you. And you might be like, that's kind of freaky. Why would they drop the floor beneath you? Well, if you're spinning fast enough, you're actually creating a lot of friction against the wall. And you won't fall because there's so much friction against you and the wall, it prevents you from falling. And so if we draw a free body diagram of ourselves, we have a wall here because we're against the wall. So I'm referencing this for my free body diagram. We have a normal force towards the center, right? Normal force is always perpendicular to the wall. Of course, we have gravity pulling us down. And it's actually friction that's keeping us against the wall, preventing us from falling. And so when we write the equations for this one, we're going to have that the normal force is our centripetal force. So we're just going to use the centripetal force equation. But instead of putting Fc, we're going to put the normal force because that's what's causing our rotation. And then we're also going to have that the frictional force is equal to F of G. Because if we're not falling, if we're not acceleration, if A equals 0, that means these two forces are balanced. It means our force up and our force down are balanced. So they must be equal to each other. And we're going to go ahead and plug in what the frictional force is. If you remember, F of F is equal to mu Fn. And so I'm going to go ahead and plug it in. Mu Fn is equal to mg. And these are our magic equations for the barrel of death. Okay. Yeah. So let's say we have a 70 kilogram rider on the barrel of death traveling at 8 meters per second. I want to find, and the radius is 6.4 meters, find mu. So we're looking for mu. And so we definitely need to use this equation. Mu Fn is equal to mg, right? But I don't know what F of n is, and I do know what the mass is, so I just don't know what F of n is. So let's see if we can find the normal force first. Well, it turns out we can. F of n is equal to F v squared over r. We know the mass, we know v, we know r, so we can find the normal force, and then we can plug it back into the left side. So normal force is equal to 70 times 8 squared all over 6.4. 8 squared divided by 6.4 should be 10. And then divide times 70, you should get 700 newtons. And so we plug it over here, mu times 700 equals 70 times 9.8. And so mu is equal to 70 times 9.8 divided by 700. And we get that mu is equal to 0.98. That's it. Really, they're not too bad. It's just a lot of equations. Thankfully, I'm letting you use the notes on this test, like all the other tests. And so what I really recommend doing, I don't know if I said this last time, get yourself a separate sheet of paper and just label, hey, horizontal problems, here's my equations that I need. Vertical problems, top, here are my equations. Bottom, here are my equations. Conical pendulum, here's my equations. Organize your notes, organize the equations, because there's a lot of them. And make it easy on you to solve the problems. Make it easy on you to take the test later with an organized cheat sheet. Okay, with that, I have no more notes. Have a great day.